Hi, everybody. Thanks for coming. Just a little bit about myself first. I love Python, of course. That's why we're all here. I do like R a little bit, not as much as Python. My background ranges from being a front-end developer to working on machine learning initiatives, particularly natural language processing. At my current job at ALGORITHMIA, I get to create fun demos on how to use machine learning in applications. I show how to productionize data models, and I write lots of deep learning docs and other documentation and blog posts. And I've been there for about 2 years as a developer advocate. And as you can see from my slides, I am not a designer. I tried that route a long time ago, and now you can see why data stuff is more my thing. So quickly, I just want to talk about Algorithmia. We're a marketplace for algorithms, functions, and models that run as scalable microservices via a common API. We're powered by a great community of developers like you all, and researchers and organizations that all contribute to the marketplace to make state-of-the-art algorithms accessible and discoverable by everyone. So think of us as the bridge that brings together the researchers who create the models and the developers who want to consume them. So if you have any questions about Algorithmia or the talk, please come find me afterwards, because I'd love to talk to everybody. So quickly, just an outline of what we're going to cover. So using OpenFace as an example face recognition model, this talk covers the basics of facial recognition and why it's important to have diverse data sets when building out a model. We'll explore racial bias in data sets using real-world examples and cover a use case for developing an OpenFace model for a celebrity lookalike app. And doing so will show how easy it is for your model to fail on homogeneous data sets. My hope is that you'll walk away understanding that even with the best intentions, anyone can fall victim to bias when building out these models. And I hope you understand after this talk the very real impacts that racial bias has in facial recognition software particularly, but also keep in mind that it's not exclusive to that domain. So first, I'd like to talk about the link between implicit and racial bias in humans and how it can lead to racial bias in AI systems. So implicit bias can affect the way we behave. This infographic refers to a field study done in 2004 by Bertrand and Mulanathan, showing the likelihood of getting through the hiring pipeline based on the whiteness of your name. They did a study where they created low-quality resumes and high-quality resumes that were fake, but they created them trying to see if there was any kind of racial bias in the hiring pipeline. They submitted them to real job ads, and it resulted in finding that it mattered more about how white the name was on the resume than the quality of the resume. So there was a bigger gap between white and black-sounding applicants on whether they moved through the hiring pipeline. Now, this is just one example of racial bias in the hiring process. But this kind of implicit bias in human behavior directly leads to us exposing those biases to the world through artificial intelligence systems that we build. So in this example, this is the output of risk assessment software called Compass by the company Northpoint. Now, their algorithm predicts the likelihood of a person reoffending and uses such factors as poverty and joblessness and other variables, although race isn't included. It's used by judges to determine sentence harshness and length. But ProPublica, an investigative journalism site, created an approximation model to gauge for racial bias in the algorithm. So you could see on this slide, when ProPublica did use their approximation model of the Compass algorithm, they scored Brisha Borden on your right at a high risk. She actually only had 4 juvenile misdemeanors, and while Vernon Prater was rated at a low risk for reoffending, although he had a lengthy record, and it included armed robberies. So 2 years later, Borden had no other offenses, while Prater had 1 grand theft auto. The model failed. The software creates almost twice as many false positives for black offenders than whites. And so This leads to the question of whether the software is teaching judges that people of color are more likely to reoffend and possibly confirming currently held biases that Black people are more likely to reoffend than white people. So you can see how important it is to keep in mind implicit bias when building out AI models. So what are the real-world applications besides recidivism software for face recognition and other biometric software? So biometric software is used for obvious cases like your fingerprint or face recognition to unlock your phone, right? We all use that. It's also used in animation to give real-life movement to characters on screen, and it's even used for personalized marketing campaigns. What might be less obvious is how facial recognition is used in security and police applications for identifying people in real time with surveillance cameras in public places. So according to perpetuallineup.org, which is a Georgetown University law site, and an article from The Guardian, LA uses 16 cameras placed in undisclosed public locations to identify citizens who have warrants out for their arrest. Police in Florida and other cities in Southern California have mobile devices with facial recognition software that they can use to match images of people driving or walking around to mugshots in their databases. So note, in Florida's case, they not only have access to those mugshots, but also DMV images of non-offending citizens. And there's a severe lack of any regulation in how police departments use these images in their databases. And some departments don't even need a reasonable suspicion to search these images. And there is no auditing, either external or internal auditing, for misuse on these images in the databases. So other cities, like Seattle, do have more stringent measures in place, and they only have mugshots in their databases versus the DMV images, like in Florida. And also they need a reasonable suspicion to search. So there's a problem with, their lack of regulation and no auditing for misuse. We don't know the model accuracy of these facial recognition models. And note that there aren't any public records on the model accuracy. However, an FBI co-authored study showed that there's evidence that facial recognition systems aren't as accurate when used on African Americans versus Caucasians. And remember, there was a high level of false positives that occurred in the approximation model that ProPublica did for recidivism software. So real-world applications lead to real-world problems. So to understand how these models fail, we need to understand how they're built, what data sets they're trained on, and note other potential areas that might result in model failure. So we're going to go through a real quick facial recognition 101. So at a high level, facial recognition software detects one or more faces in an image. It separates that face from the background, and it also detects multiple faces in an image. It normalizes the position of the face. For instance, if faces are looking diagonal or upward, it normalizes the position so all of them are facing forward. And then it gets thrown into a neural net for facial feature discovery. And when it's ready for classification, it's used to compare a face in an image to faces in a database, like the DMV database or the mugshot database, to see if there's a match. So here we have two actors from the old show True Blood, who are classified as themselves by a facial recognition model called OpenFace. So OpenFace is an open source deep learning facial recognition model, and it's based off the paper FaceNet by some folks at Google, and is implemented using Python and Torch. And it's great because it can run on both CPU or GPU environments. So OpenFace is only a couple of years old, but it's been widely adopted because, one, it's open source, and it also offers a level of accuracy that's comparable to private state-of-the-art systems like Facebook's DeepFace or Google's FaceNet. So what's particularly nice about OpenFace is that the development of the model focuses on real-time training and classification on mobile devices, so you can train on very little data on the fly. And in fact, the images of the actors in this slide were trained on only 10 images each, and they were correctly classified on new images that the model hadn't seen before. So training initially is done offline using Torch, It's done by the folks at OpenFace. They used 500,000 labeled images, and the images came from two open source data sources. It can be more generalized than the models, such as DeepFace from Facebook, because Facebook only trained on their own internal private data set. So their model would not generalize to the public if they ever release that. Then those images are thrown into the neural net for feature extraction using Google's FaceNet inception model, which results in 128 facial features that are embeddings in a Euclidean space that represent a generic face. Then FaceNet's triplet loss function is used to gauge the accuracy of the model, and it also enables clustering of like images, which speeds up the classification process later on. So then Python is used to send images through a library called dlib for facial detection, and again, that means it's separating the face from the background, or separating faces from multiple faces in the image, and that produced 68 facial landmarks. And then OpenFace uses OpenCV's affine transformation for normalization of the face's positioning. Remember, we talked about that all the faces need to be facing the same direction. It's then cropped to 96 by 96 pixels for input to the trained neural net. Then you use that trained neural net in a single forward pass that gives you 128 facial embeddings of low-dimensional data, making for faster classification. So here's our use case. We're going to think through a celebrity lookalike app to see what true blood characters we most look like. The reason I chose True Blood is that the show had a fairly diverse cast, which is the crux of our racial bias issue in AI, having data sets that don't correctly represent real-world conditions. First, let's talk about the training data. So again, OpenFace it only needs 10 images to give a fairly accurate result. Of course, you could use more, but again, it's made for mobile development on the fly. And so I chose to use only 10 images for each actress that had faces in various lighting, quality, and position. Although note that a lot of these differences are normalized by dlib and OpenCV. The next step in our pipeline would be running the images through the trained neural net to get the 128 facial embeddings used for classification to get that low-dimensional face representation. And then for the classification portion of using OpenFace, in this use case of building a celebrity lookalike app, you would probably want to use a clustering algorithm instead, because you're looking for similarity between faces and not a direct match. But Algorithmia, we already had an OpenFace classification model using a support vector classification. So I used that to get the highest confidence score for my trained model's prediction. So my first implementation, I trained again on 10 images for each of the top 5 main actresses from True Blood. But note that although their whole cast over time is diverse, the top 5 actresses are all Caucasian except for one African-American actress called Rutina Wesley. And so here is a match for Joanna Gaines from HGTV, who is predicted to be Carrie Preston, the waitress from Bellefleur's bar. And I think we can all agree that it's not a great match, and that their facial landmarks are quite different from each other, especially their face and eye shape. Something to note is that the pre-processing step in dlib converts to grayscale, so it doesn't see race. It produces 68 landmarks that are fed into the neural net. So the neural net doesn't see skin color, and when we pass our image through the trained neural net, we get the 128 facial embeddings used by the SVM classifier. So it's just looking at facial feature measurements. Even though skin color isn't in our feature space, certain ethnic groups or races share more similar features with each other than they do with those not in their ethnic group. For instance, a study called Ethnic Identification from Face Images by Zhao Guang Lu and Anil K. Jain found that Chinese had the whitest faces in intercanthal space, which is the space between the eyes. And that was out of a sample space of Chinese, African American, and North American Caucasians. Not surprisingly, according to a PBS article on AI bias called Ghosts in the Machine, cited that research had shown that models that are built in Asia, presumably trained on Asian faces, more accurately predicted, they more accurately classified Asian populations versus Caucasian populations, and vice versa. And so it highlights the need for diversity in your training data to reduce the likelihood of sampling bias. So since I wasn't satisfied with the results of the trained model using the 5 main actresses from Trueblood, I changed up the diversity makeup of the training set. So to keep the sample size the same, I removed 3 of the main actresses that were from my original data set, but I kept Carrie Preston, who Joanna Gaines was originally classified as, and I kept another Caucasian actress, Kristen Bauer. I then added 3 actresses that were more ethnically diverse, but they weren't main characters. Our newly trained model predicted that Joanna Gaines was classified as Fidette Lim. Subjectively, it seems their facial features are more similar. As you know, you could see their face shape and their eye shape and their intercanthal shape is more similar to each other than Joanna Gaines was to the previous actress, Carrie Preston. Now, while the classification, if you're paying attention to the confidence scores, they're pretty low, remember that we're noodling this model to be used as a clustering algorithm looking at similarity versus what it actually is used for classification. And also, if you were paying attention to the confidence score from Joanna Gaines' first match compared to the second match, you'll notice that the first score is actually higher, the one that she was classified as Carrie Preston. But you have to remember that you need to disregard any previous predictions that you got from training on your first model, because now you've got a completely different trained model on a different data set, so you can only compare your confidence scores within that trained model. So I hope you could see that when the distribution of your training data is dissimilar to your testing or real-world data distribution, then your model won't give you accurate results, as when training on a more diverse data set that better represents real-world conditions. So model failure and what we can do to mitigate any kind of implicit or racial bias in our models. Our goal is to create the most accurate models we can. So I think it's obvious now that diverse training sets gives you more accurate models, but getting diverse training sets isn't as easy or as intuitive as you might think. Many researchers building out these models, like the folks at Carnegie Mellon that produced OpenFace, only have access to public open source images because it's both time-consuming and very costly to create labeled data sets themselves. So they have to use what's out there, which might not be as diverse of data sets as they wish for. Also, if you're extracting your own data, think through how your data extraction methods can potentially lead to homogeneous data sets. If you were really to build a celebrity lookalike app, you'd probably want more images than just from Trueblood. So if you were to go to a site like IMDb, who has celebrities, they're actually sorted by popularity. So if you were to scrape the first 2,000 images, you're not gonna get the most diverse data set. A lot of top celebrities are Caucasian. It's a very homogeneous data set. So I suggest mixing it up and getting maybe a third of the top, a third of the middle, a third of the bottom, or however you wanna randomize that a little bit better so you get a more diverse data set. Also, you've got to think about how others are getting their data. So OpenFace actually uses DLib for face detection, which we talked about, and now that was trained on labeled faces in the wild data, which is a public data set, and that was scraped from the internet about 10 years ago using Viola Jones face detection, which uses what's called a Haar cascade classifier, which is not a state-of-the-art face detection algorithm anymore. Most people use HOG. And so this could account for differences in demographics. I mean, there's probably different diversity levels from now to 10 years ago. And note that there's no ethnic distribution data, no statistics for labeled faces in the wild. It simply states on their site that they're a diverse data set. And lastly, OpenFace Model is tested, their accuracy is tested on labeled faces in the wild, and that's, again, the same data set used to train DLib for face detection. So you've got to pay attention to how you're gathering your data and how other people are too when you're relying on open source data sets. And your testing data is equally important in order to test for real world conditions. So we usually split the training set into 80-20, 90-10, into training and testing data sets. But if your original data set isn't that diverse, your model's not going to perform well on real world conditions. So I think that a way to mitigate that is, if you have any questions about how diverse your data set is to look for underrepresented people in the population and test on them. And then you have to ask yourself, what do I do from there if my model's failing on those underrepresented groups? So you have to ask yourself, who's using your model? A lot of times you don't know, so assume everyone. And yes, it's expensive and time-consuming to gather diverse training data like we talked about, and a lot of us only have access to public data sets. But again, you don't initially have to. Just first test on underrepresented groups, and then ask yourself who your user will be and whether it's worth taking the risk of alienating groups and putting out a really poorly performing model. So quoting my coworker from this morning about accepting model failures, he said, if foxes get mislabeled as cats 30% of the time, it isn't going to spill anyone's milk. But note that Google is still trying to fix their object detection algorithm for Google Photos that classified Black people as gorillas. Their initial fix has been to remove certain labels, such as the term gorillas, then fix the diversity of their object detection model. So, and last, another way to mitigate poor model performance on racially diverse real-world conditions is to ask yourself, is my own team diverse? So a lot of times, some of these racial bias issues come from homogeneous teams. And note that the PBS article, Ghosts in the Machine, a woman, Mrs. Bualamini, a Black PhD student at MIT, had to put on a white mask to enable facial recognition algorithms to be able to track her face. And while working on another project, her white classmates had no trouble with facial detection algorithm, which failed on her face. So she noticed that there was a problem and took steps to bring about awareness of this issue in racial bias and facial recognition. So it brings me to the point that when testing out these models, research teams and other developers many times will test on their own images, or at least if it's a diverse team, they might catch an issue with the training data sooner than if your team is homogeneous. Because diversity increases unique perspectives that help us build smarter applications and models. Thank you very much. We're wrapping up.